Every galaxy carries within it a kind of life story, beginning with turbulent youth and ending in a long and quiet old age. In their early eras, galaxies are crowded with bright, blue, short-lived stars, born in rapid bursts from dense clouds of gas. Over billions of years, this gas is slowly used up, blown away, or heated until it can no longer collapse to form new suns. Astronomers call a galaxy that has largely stopped forming stars a quenched or passive galaxy. It still contains stars, sometimes hundreds of billions of them, but their average age grows steadily older. When star formation declines, the overall color of the galaxy slowly shifts from bluish to yellow and eventually toward a softer reddish glow. The galaxy does not shut off overnight. Star birth fades region by region, spiral arms lose their sharp, bright definition, and gas clouds thin out. What remains is a vast collection of aging stars, orbiting in a gravitational ballet that continues, even as the galaxy's youthful brilliance slips into memory. Star formation depends on cold, dense reservoirs of hydrogen gas and dust. Inside spiral galaxies, this gas collects in long, dark lanes that trace the arms, forming nurseries where gravity can pull matter together into new stars. Over time, stellar winds, supernova explosions, and the radiation from hot young stars stir and heat this gas. Powerful outflows driven by central black holes can also sweep material out of the galaxy's inner regions. Some gas escapes entirely into intergalactic space. Some remains, but becomes too warm and too diffuse to collapse efficiently. Gradually, the galaxy's supply of star-forming fuel declines. In many massive galaxies, especially in clusters, this process has largely finished. They contain very little cold gas and form only a few new stars each year or fewer. The galaxy still shines, but almost all of its light comes from stars that were born long ago. The age distribution shifts, like a city whose youngest residents have moved away, leaving only mature and elderly inhabitants to occupy its streets. Young, massive stars burn hot and blue, pouring out light and ultraviolet radiation. They live brief lives, often only a few million years, before exploding as supernovae. Older, lower-mass stars glow more gently in yellow, orange, and red tones, and can endure for billions or even trillions of years. When a galaxy is vigorously forming stars, it contains many hot blue giants, and their brilliance skews the whole galaxy's color toward the blue. After star formation slows, these massive stars die off relatively quickly, while the longer-lived, cooler stars remain. Over a few 100 million to a few billion years, the collective light shifts toward redder wavelengths. In galaxy surveys, this change appears as a separation between a blue cloud of star-forming galaxies and a red sequence of quiescent systems. Crossing from one to the other is a sign that star formation has largely ceased. The galaxy still holds its structure, but the youthful blue sparkle fades, replaced by the softer, steadier glow of stellar middle and old age. Inside a star-forming galaxy, glowing nebulae mark the locations of active stellar nurseries. These regions, often called HII regions, shine as ultraviolet light from young stars ionizes hydrogen gas, causing it to emit a characteristic pinkish or reddish glow. As star formation comes to an end, these nebulae become more rare. Without a constant supply of massive newborn stars, the gas is no longer strongly ionized, and the bright emission fades. The underlying cold molecular clouds can still exist for a time, but they may be shredded by old supernova shocks or gently dispersed by gravity and pressure. In a quenched galaxy, wide fields of diffuse starlight replace the patchwork of bright nebulae. Long exposure images sometimes reveal faint filaments and wisps, echoing past periods of activity like ghostly reminders of long-ended bursts of star birth. The galaxy's interstellar medium becomes calmer, less turbulent, more uniform. Fireworks give way to embers, and the once dramatic contrast between dark lanes and brilliant nebulae slowly smooths into a quieter cosmic canvas. When a galaxy stops forming stars, its existing stellar population begins to age in place. The most massive stars are the first to go. Even if star formation has almost ceased, some young giants still remain from the last wave of births. These stars, perhaps tens of times the mass of the Sun, exhaust their nuclear fuel quickly and end their lives in core collapse supernovae. For a short period, the galaxy may still experience occasional brilliant explosions. Each one briefly outshines the combined light of billions of stars. Over tens of millions of years, however, this remaining population is spent. The rate of bright, massive supernovae falls. What remain are intermediate mass and low mass stars, which evolve more slowly, swelling into red giants and planetary nebulae on timescales of hundreds of millions to billions of years. The galaxy's most dramatic, short-lived actors leave the stage early, leaving behind a quieter ensemble cast of long-lived suns, glowing steadily and less violently than their brilliant predecessors. As stars like the Sun grow old, they eventually shed their outer layers, leaving behind dense cores known as white dwarfs. These objects pack roughly the mass of the Sun into a sphere about the size of Earth. In a galaxy where star formation has largely stopped, white dwarfs accumulate over time. Each one shines with leftover heat, gradually cooling and fading over billions of years. The galaxy's stellar population quietly shifts toward these compact remnants. From a distance, this change is subtle, because white dwarfs are faint compared with ordinary stars. Yet in number they can be significant, forming a kind of fossil record of past generations of star formation. Over very long stretches of cosmic time, white dwarfs themselves will cool to near invisibility, turning into theoretical objects sometimes called black dwarfs. No such truly cold remnants are expected yet, because the universe is not old enough. Still, every quenched galaxy carries the seeds of this future, in the growing congregation of its white dwarf stars. Not all stars end as white dwarfs. The most massive ones leave behind neutron stars and black holes. Neutron stars are city-sized, ultra-dense remnants where matter is compressed beyond atomic structure. Black holes are regions where gravity is so strong that not even light can escape. In an aging galaxy, these compact remnants steadily accumulate. Most are dark and hard to detect, unless they interact with nearby matter or orbit a companion star. Over time, countless stellar mass black holes and neutron stars drift through the galactic halo and disk, forming an invisible skeleton of degenerate matter. Occasionally, pairs of such objects merge, releasing bursts of gravitational waves that ripple through space-time. Events like these become less frequent as massive stars disappear, but their products remain. The galaxy retains both its visible population of long-lived stars and a hidden underworld of dark remnants. This balance slowly tips, as new bright stars appear less often, and the archive of quietly orbiting remnants steadily grows. Many galaxies harbor supermassive black holes at their centers, with masses ranging from millions to billions of suns. When gas falls toward these objects, it heats up and can emit tremendous energy as an active galactic nucleus or quasar. This energy is capable of pushing gas outward or heating it so that it resists collapse. In some galaxies, this feedback helps shut down star formation by preventing cold gas from collecting in the central regions. Outflows and jets, extending for thousands of light years, can be observed in radio and X-ray light. As the supply of infalling gas dwindles, the central engine gradually subsides. A once blazing quasar can fade into a relatively quiet nucleus, with only occasional flickers when a cloud or a star wanders too close. Even in this quieter state, the central black hole continues to grow slowly. It swallows stars and gas at a reduced rate, deepening the gravitational well, while the wider galaxy around it dims and grows older. The environment of a galaxy plays a major role in how and when it stops forming stars. In dense galaxy clusters, galaxies plunge through hot intracluster gas as they orbit. This can strip away their own gas in a process known as ram pressure stripping. Tidal interactions and past mergers also disturb their gas reservoirs. Observations show that many large cluster galaxies, especially near the center, are massive, reddish ellipticals with very low star formation rates. Their shapes are smooth, lacking sharp spiral arms, and their light is dominated by older stars. Some still host faint filaments of cooling gas or small pockets of star birth, but these are subdued compared with the past. Over billions of years, clusters assemble more and more quenched galaxies. The cluster's combined light therefore shifts toward red and near-infrared wavelengths, even as the total mass in stars and dark matter continues to grow. The cluster becomes a kind of archive of galactic old age, where stellar populations are mature and star-forming fuel is scarce. Many quenched galaxies take the form of ellipticals, rounded, smooth systems lacking prominent disks or spiral structure. These galaxies are often the product of past mergers between spirals and smaller companions. During these interactions, gas can be driven rapidly into the center, igniting intense but relatively brief bursts of star formation. Afterward, much of the cold gas may be exhausted or heated, and further star formation slows dramatically. The resulting galaxy contains a wide range of stellar orbits, forming a roughly ellipsoidal swarm rather than organized, rotating arms. In large ellipticals, the stars are predominantly old, with ages of several to roughly 10 billion years or more. Their spectra show signatures of aging stellar populations and little evidence of ongoing birth. The galaxy glows with a uniform, diffuse light, like a city of long-established neighborhoods. Subtle gradients in color and brightness record ancient histories of mergers and starbursts, even as the present moment is one of relative calm and stellar stability. Nebulae, the luminous clouds that decorate images of star-forming galaxies, are transient structures on cosmic timescales. Emission nebulae require a population of nearby hot stars to keep their gas ionized and glowing. Reflection nebulae depend on dust grains to scatter starlight. As star formation shuts down, the supply of massive, luminous stars dwindles. Without their radiation, many nebulae rapidly lose their brightness, fading into the background interstellar medium. Planetary nebulae, formed from dying sun-like stars, also appear for only tens of thousands of years before dispersing. In a galaxy where most stars are old and low mass, fewer such objects are being created. The combined result is a diffuse, smoother glow, with fewer sharp, colorful knots. If one could watch a time lapse over hundreds of millions of years, the transformation would resemble fog lifting from a landscape, revealing the underlying distribution of stars. The grand arches and pillars captured in familiar images would gradually dissolve, leaving behind a quieter, more uniform galactic sky. As galaxies age and their hottest, bluest stars vanish, their remaining light leans strongly toward red and infrared wavelengths. Older stars emit more of their energy in these longer wavelengths, and interstellar dust can absorb shorter wavelength photons, irradiating the energy in the infrared. Over time, as the universe expands, even this light is stretched to longer wavelengths by cosmic redshift. Distant, early galaxies already appear redder because their light has traveled for billions of years through expanding space. In the far future, a quenched galaxy's spectrum will be concentrated in the infrared and radio bands, faint and diffuse. To instruments tuned to visible light, the galaxy would seem dim, perhaps invisible against the background. Yet energy is still present, spread thinly across the spectrum. The changing color of galaxies, and of the universe as a whole, traces the slow cooling and aging of cosmic structures, as the brilliant blues of youth give way to the softer, deeper tones of an older cosmos. On the largest scales, astronomers can estimate how quickly new stars are forming across the entire observable universe. Observations show that this cosmic star formation rate peaked roughly 10 billion years ago. Since then, it has declined by more than an order of magnitude. This means that, averaged over all galaxies, the universe is already far past its most productive era of star birth. Many massive galaxies are largely quenched, while smaller systems still form stars more actively, especially in less crowded environments. As time passes, more galaxies exhaust or lose their gas, transitioning from blue star-forming systems to redder passive ones. The cumulative effect is a universe that is gradually shifting from a place filled with young, brilliant stars to one dominated by older, longer-lived ones. This process is slow on human timescales, unfolding over billions of years. Yet it marks a deep change in the character of the cosmos, as the total amount of fresh starlight being generated steadily diminishes with time. Even as star formation wanes, the existing population of low-mass stars promises a long stellar future. Red dwarf stars, smaller and cooler than the Sun, burn their fuel slowly and can remain on the main sequence for trillions of years. The universe is not yet old enough for any such star to have completed its life. In quenched galaxies, many of these faint red dwarfs already dominate by number, even if they contribute modestly to the total brightness. Over unimaginably long times, they will carry the torch of starlight, long after more massive stars have faded. Occasionally, gravitational encounters in dense regions may lead to new star formation through stellar collisions or by concentrating gas left from past generations, but these events are expected to be rare. The overall trend is a steady decrease in the number of luminous, short-lived stars, and a slow drift toward a cosmos lit mostly by these small, steady embers scattered across ancient galaxies. Looking far ahead, theoretical models suggest a universe that grows darker and quieter as galaxies age. As the last reserves of cold gas are consumed or dispersed, large-scale star formation essentially ceases. Existing stars evolve, leaving behind white dwarfs, neutron stars, and black holes. Over timescales vastly exceeding the current age of the universe, even white dwarfs cool to near invisibility. Occasional mergers and accretion events continue, but the average brightness of galaxies declines. The night sky, as seen from any surviving planet, would contain fewer bright points and more faint, reddish stars. Eventually, black holes may dominate the mass locked in compact objects, slowly evaporating over even longer spans through Hawking radiation, according to quantum theory. The overall picture is of a cosmos moving from a hot, bright, star-forming youth toward a cold, diffuse, and sparsely lit old age. Galaxies that once blazed with newborn stars become archives of ancient light, their remaining glow stretching thinly into the deepening cosmic night. As star formation slows and then stops, the once bright disks of spiral galaxies begin to grow optically thin. The dense knots of blue stars disperse over hundreds of millions of years, leaving behind a smoother, fainter glow dominated by older, redder stars. The spiral arms, which depended on ongoing waves of starbirth to remain sharply traced, soften into more subtle structures that are difficult to distinguish even with powerful telescopes. Dust lanes that once hid and reddened starlight are slowly eroded by radiation, stellar winds, and supernova shocks, then no longer replenished. Over time, the interstellar medium in the disk transitions from cold, clumpy clouds into a more uniform warm gas that cannot easily collapse again. The visible surface brightness of the galaxy decreases, while its size may appear to grow slightly as long-lived stars drift outward through gravitational interactions. From a distance, such a galaxy takes on a more ghostly aspect, with a low-contrast disk surrounding a somewhat brighter central bulge that still holds many stars. Within these aging galaxies, star clusters undergo their own quiet transformations. Young, massive clusters that once shone with thousands of hot blue stars lose their brightest members first as they explode or fade into compact remnants. The remaining stars, mostly less massive and longer-lived, continue their orbits within the cluster, but gravitational nudges between them gradually alter their paths. Over billions of years, these small perturbations allow some stars to gain enough speed to escape the cluster's pull entirely. The cluster slowly evaporates into the surrounding galaxy, leaving behind only the most tightly bound cores or dissolving completely. Even the ancient globular clusters that orbit in a galaxy's halo are not entirely immune. Tidal forces from the galaxy's mass distribution, and sometimes from close passes with the galactic center or other clusters, strip away outer stars. The night sky inside such a cluster would change immeasurably slowly, but on cosmic timescales, these dense swarms of stars thin out, adding their light to the diffuse stellar background. As star formation grinds to a halt, one of the key processes is the heating of galactic gas to temperatures where it can no longer collapse. Supernova explosions, stellar winds, and energetic outflows from central black holes all contribute to raising the temperature of the interstellar and intergalactic medium. Gas in galactic halos can reach temperatures of roughly 1,000,000 degrees or more, forming a thin, hot atmosphere that emits primarily in X-rays. At these temperatures, individual atoms move rapidly, and random motions overwhelm the gentle pull of gravity trying to draw the gas back into cold clouds. Without efficient cooling through radiation, the gas remains suspended in this energetic state. In galaxy clusters, this hot intracluster medium can contain more mass than all the stars combined, glowing faintly in X-rays while remaining invisible to human eyes. The raw material for future stars has not vanished, but it has settled into a form that is difficult to reuse, locked in a long-lived, heated reservoir. In a galaxy where star formation has ceased, the main story shifts to the choreography of orbits. Every star, white dwarf, neutron star, and black hole follows a path defined by the galaxy's overall gravitational field. Over billions of years, near encounters and the combined tug of many neighbors gradually alter these orbits. In the disk, spiral patterns that once organized stellar motions fade as the density waves weaken without fresh gas to respond to them. Stars may drift radially, moving inward or outward by thousands of light years through a process sometimes called radial migration. In the central regions, stars experience stronger gravitational perturbations, and some are scattered onto elongated or inclined orbits. Encounters with massive objects, such as giant molecular clouds in earlier epochs or compact remnants later on, gently randomize motions. The galaxy's structure becomes more kinematically mixed, with fewer stars on perfectly circular paths. The overall appearance remains stable, but beneath the surface, every orbit traces a slightly evolving story within a slowly changing gravitational landscape. Even as the large-scale drama calms, the small-scale interactions between stars continue. A significant fraction of stars form in binary or multiple systems, orbiting a common center of mass. Over time, as stars evolve off the main sequence, these systems can undergo subtle but important changes. When one star expands into a red giant, it may transfer material to its companion. This mass exchange can spin up the receiving star, alter its lifetime, or even ignite new nuclear burning phases. White dwarfs in close binaries can accrete material, occasionally leading to novae, or in some cases, thermonuclear supernovae that briefly reignite a galaxy's fading light. In wider binaries, the slow loss of mass through stellar winds can change the orbital separation, gently widening or tightening the orbit. Although the overall number of luminous events decreases in a galaxy with no new stars, these residual binary interactions maintain a background level of variability, ensuring that the galactic light curve never becomes perfectly smooth. In a galaxy that has stopped forming stars, massive stars vanish first, so core-collapse supernovae eventually cease. What remain for a while are the delayed explosions from white dwarfs in binary systems, often categorized as Type Ia supernovae. These events can occur long after star formation has ended, because they depend on the slow accumulation of mass onto a white dwarf or the merger of two white dwarfs in a tight orbit. Over billions of years, the rate of such supernovae declines as the supply of suitable systems is gradually exhausted. Each final explosion briefly rivals the brightness of the entire host galaxy, momentarily reversing the trend toward darkness. However, the afterglow fades over months and years, leaving only an expanding shell of hot gas and heavier elements. Eventually, even these delayed detonations become extremely rare, and the galaxy enters an era with virtually no new supernovae, only the quiet cooling of remnants formed long before. The lives and deaths of stars create heavy elements, from carbon and oxygen to iron and beyond. When star formation ends in a galaxy, this chemical enrichment process slows dramatically. The last generations of massive stars and supernovae have already seeded the interstellar medium with metals, and many subsequent stars have incorporated this enriched material into their atmospheres and planets. Without new stars forming, there are fewer fresh sites where nuclear fusion can further transmute lighter elements. Some additional heavy elements continue to arise in rare events, such as neutron-star mergers, but their overall contribution becomes modest compared with earlier epochs. The galaxy's average metallicity, once rising with each new cycle of starbirth and death, approaches a near-constant value. Heavy elements become increasingly locked inside long-lived low-mass stars, white dwarfs, planets, and compact remnants. The great cosmic experiment in element building enters a phase of diminishing returns, with most of the periodic table already well represented and little new variation added over time. Interstellar dust, composed of tiny grains of carbon, silicates, and other compounds, plays an important role in star-forming galaxies by cooling gas and helping clouds collapse. In galaxies where star formation has ceased, dust follows a slower, more fragile evolution. Supernova shocks and strong radiation fields that once both created and destroyed dust become less common, altering the balance of processes. Existing dust grains continue to be eroded by collisions in hot gas, a process called sputtering, gradually reducing their size and mass. Without the steady replenishment from dying massive stars and evolved giants still forming in large numbers, the overall dust content declines. Over long timescales, regions that were once filled with dense, dark lanes clear, and starlight passes more directly through the galaxy. The reddening of light by dust diminishes. Astronomers observing such a system see a cleaner, though fainter, stellar spectrum, with the intricate interplay between gas, dust, and young stars replaced by a simpler, more transparent stellar environment. As the bright disks and star-forming regions of galaxies fade, the extended stellar halos and dark matter halos become increasingly important to their overall structure. Stellar halos contain ancient, metal-poor stars and globular clusters that trace the early assembly of the galaxy through mergers and accretion. These stars are spread over a vast volume, sometimes extending hundreds of thousands of light-years from the galactic center. Their faint glow is often overwhelmed by the central light in younger, more active galaxies. In quiescent galaxies, the contrast shifts. Halos, though still dim, represent a more significant fraction of the remaining visible light. Meanwhile, the dark matter halo, which has always dominated the mass budget, continues to shape the motions of stars and remnants. With little new baryonic activity to rearrange matter, the large-scale gravitational potential stabilizes. The galaxy becomes a mature system, where most of the visible mass resides in long-lived stars orbiting quietly within a nearly unchanging dark matter framework. On scales above individual galaxies, galaxy clusters themselves evolve even as their members stop forming stars. Over time, smaller clusters and groups fall together under mutual gravity, merging into larger, more massive structures. The central galaxies of these clusters, often already quiescent ellipticals, can grow through a series of mergers with other depleted systems. Each merger adds stars, dark matter, and depleted gas, but seldom large amounts of cold, star-forming material. The resulting central giants become enormous, roughly hundreds of thousands of light-years across, yet remain dominated by old red stars. The intracluster medium, heated during the violent assembly process, stays hot and resistant to cooling. Some cooling may occur, but energetic feedback from central black holes can prevent large-scale star formation from reigniting. Thus, the largest structures in the universe become vast cemeteries of galaxies, where growth continues mostly by combining already aged systems rather than by birthing new stars from pristine gas. As galaxies and clusters merge, so do their central black holes, though often after long delays. When two galaxies with dormant or weakly active galactic nuclei combine, their central black holes sink toward the new shared center through dynamical friction, dragging surrounding stars along. Eventually, they form a binary black hole system. Over millions to billions of years, interactions with stars and gas extract energy from the orbit, bringing the pair ever closer. When the separation becomes small enough, emission of gravitational waves carries away the remaining orbital energy, and the black holes merge in a brief, intense burst of spacetime ripples. These events are invisible in light, but can be detected through gravitational wave observatories. In an aging universe with fewer bright sources, the energy output of such mergers remains an important sign of continuing dynamical activity. The merged black hole becomes more massive and may receive a recoil kick, oscillating through the galaxy's core before settling back toward the center. Even as new light sources diminish, the universe retains a persistent background of relic radiation. The cosmic microwave background, already stretched into millimeter wavelengths by cosmic expansion, continues to cool and lengthen in wavelength. Starlight emitted in earlier, more active epochs travels through space, redshifting into infrared and eventually radio bands. In contrast, galaxies that have ceased forming stars contribute a steadily declining share of fresh photons to this cosmic sea. Their role shifts from producers of new light to custodians of existing light, slowly radiating stored energy as their stars evolve and remnants cool. Over immeasurably long durations, the overall photon density in the universe decreases relative to non-radiative forms of energy. Light becomes both lower in energy and more sparsely produced, though it still fills space. These relic photons preserve a record of past activity, carrying information about vanished galaxies and long-faded nebulae, even as the present-day universe grows quieter and optically darker. In galaxies where no new stars form, the existing stellar remnants begin an extended, shared journey of cooling and fading. White dwarfs, initially extremely hot, radiate their stored thermal energy into space over tens to hundreds of billions of years, gradually dimming from visible light into infrared and eventually into the microwave regime. Neutron stars, though compact and dense, also cool and lose their surface heat, their emission becoming weaker and harder to detect. Black holes, by their very nature, do not radiate in ordinary ways, though they can slowly lose mass through Hawking radiation on timescales far beyond current cosmic age estimates. The combined effect is that, one by one, the luminous signatures of stellar remnants slip below detectability. Photons continue to emerge, but in progressively longer wavelengths and ever smaller quantities. The stellar genealogy of a galaxy, once legible in bright and colorful stages, becomes encoded in almost invisible embers spread across vast volumes of space. As the universe ages and star formation declines across cosmic time, each galaxy gradually becomes more like a fossil record than an active workshop. Its stars, remnants, and chemical composition preserve a history of past mergers, bursts of star formation, and energetic events. Astronomers reading that record through stellar populations and elemental abundances can reconstruct when the galaxy was most active, how quickly it enriched itself, and how it interacted with its environment. In a future where almost all galaxies have ceased forming stars, such forensic analysis would remain possible in principle, though the objects studied would be older, cooler, and dimmer. The variety of galactic forms and histories would still exist, but the processes that once actively reshaped them would have slowed to a crawl. The universe, taken as a whole, would resemble a vast museum of long-completed structures, where change continues, but at a pace measured in timescales far exceeding the current age of cosmic structures. Through all these stages, from the quenching of star formation in galaxies to the cooling of individual remnants, the overarching trend is a slow approach toward darkness. This is not an abrupt transition, but a gradual shift in balance. Regions that once blazed with ultraviolet light become red, then infrared, then nearly invisible. Gas that once glowed in emission lines settles into faint, diffuse halos. Black holes grow in mass while producing fewer luminous outbursts. Star clusters thin, spiral patterns blur, and the universe's energy moves inexorably from short-wavelength, high-frequency radiation into long-wavelength, low-energy backgrounds. Yet the structures built during the active era persist, stretched and cooled, but still present. The night skies over hypothetical future worlds would hold far fewer bright points, but their underlying gravitational framework would remain, a lattice of galaxies, clusters, and filaments. The path from a young, radiant cosmos to a dimmer, quieter one is a story of transformation rather than simple extinction, governed by the long, patient timescales of cosmic evolution. After the bright blue stars have burned out and the medium-mass suns have faded into white dwarfs, the smallest stars continue their quiet work. Red dwarfs, with masses below roughly half the sun's, burn their hydrogen fuel with remarkable frugality. Many will shine for hundreds of billions or even trillions of years. In a galaxy where star formation has ceased, these faint red points become the dominant sources of starlight. They are cooler and dimmer than stars like the sun, radiating most of their energy in deep red and infrared wavelengths. Their planetary systems, if any remain stable, orbit under a subdued and steady glow. Gradually, as more luminous stars wink out, the background sky in such a galaxy becomes defined by these long-lived embers. The galaxy still contains stars, but its character changes from a place of bright, short-lived brilliance to one of patient endurance. The cosmic story slows, stretching across timescales that dwarf the current age of the universe, supported by these resilient, low-mass suns. In galaxies where no new stars are born, many planets continue to orbit their aging stellar hosts. Around sun-like stars that have already passed through red giant phases, inner planets may have been scorched, engulfed, or stripped of atmospheres. Outer planets can survive as cold worlds circling a white dwarf, illuminated by a pale, compact star that shines intensely but with far less total power. Around long-lived red dwarfs, planets persist under dim, ruddy skies. Over immense timescales, orbits can slowly change under subtle gravitational tugs from passing stars and remnants. Some planets are ejected into interstellar space, becoming lonely rogue worlds drifting through the dark galaxy. Others spiral inward due to tidal interactions, edging closer to their fading suns. Without frequent bright supernovae or strong ultraviolet radiation, planetary atmospheres may stabilize or slowly leak into space, molecule by molecule. The diversity of these ancient planetary systems becomes a quiet archive of earlier, more active eras, preserving scars from past bombardments and traces of long-vanished stellar neighbors. As a galaxy ages and gravitational encounters accumulate, more planets are nudged out of their original systems. Close passes between stars, or the violent reshaping that follows a supernova or stellar merger, can unbind planets completely. These worlds become rogues, drifting without a central star. In a galaxy that has stopped forming stars, such rogue planets may slowly grow in number compared with the remaining bright stellar systems. Their surfaces are lit only by the distant, diffuse glow of the galactic background and the faint light of the cosmic microwave background. Any warmth they retain comes from internal heat left from formation, radioactive decay in their interiors, or, in rare cases, from thick insulating atmospheres. Many will be gas giants wrapped in frigid clouds, others will be rocky, ice-covered spheres. They orbit the galactic center directly, like dark, isolated ships on a wide sea, responding only to gravity. These unlit worlds contribute mass, subtly shaping the orbits of stars and remnants, yet remain almost impossible to see. With no massive young stars pouring out ultraviolet radiation and stellar winds, the interstellar medium in a quiescent galaxy begins a long cooling phase. Hot gas in the halo remains energized by old shocks, ancient outflows, and the deep gravitational well of the galaxy, but denser gas within the disk slowly radiates away its heat. It emits in infrared and submillimeter wavelengths, giving up energy photon by photon. Over vast spans of time, the average temperature of the space between stars drops. However, the gas does not easily condense into new stars because its overall density has become too low and many potential birthplaces have been disrupted. Occasional gravitational instabilities may still trigger small pockets of collapse, but these become rare and minor compared with earlier epochs. The interstellar medium transitions from a lively, multi-phase environment full of ionized bubbles and shock fronts into a calmer, more uniform mixture. This chilled, diffuse gas remains as the quiet background through which stellar remnants and remaining stars drift on their slow orbits. Galaxies host large-scale magnetic fields woven through their disks and halos by the motions of gas and stars. In young star-forming systems, supernova explosions and turbulent gas flows continuously stir and amplify these fields. When star formation ceases, the primary drivers of turbulence weaken. The gas calms, but the magnetic structures remain embedded in the interstellar medium. Over time, differential rotation of the galaxy slowly stretches and rearranges the field lines. Without strong turbulence, the magnetic field may become more ordered on large scales, arching smoothly through the disk and halo. Charged particles still spiral along these invisible lines, emitting faint radio waves as they do. The overall magnetic strength can decline as energetic processes fade, yet it does not vanish quickly. Instead, the ancient magnetic skeleton of the galaxy persists as a kind of memory of its more active past. These old fields influence how gas drifts, how cosmic rays move, and how the last traces of interstellar matter settle within the aging system. High-energy particles called cosmic rays are accelerated by supernova shocks, stellar winds, and jets from black holes. In a galaxy with no new massive stars exploding, one of the main engines of cosmic ray production falls silent. The remaining sources are older, lingering shocks from past events, and in some cases, low-level activity around the central black hole. Over eons, the population of the most energetic cosmic rays thins. They scatter off magnetic fields, gradually losing energy through interactions with gas, radiation, and fields. The spectrum of cosmic rays shifts toward lower energies, and their ability to ionize and heat the interstellar medium weakens. This slow decline further encourages cooling and calm within the galaxy. Yet cosmic rays never disappear entirely. Even low-energy particles continue to thread through interstellar space, faint tracers of long-finished explosions. The once vibrant interplay between cosmic rays, gas, and magnetic fields settles into a subdued balance, another sign that the galaxy has transitioned from a youthful, active phase into a long, quiet maturity. Galaxies emit not only visible light, but also radio waves and X-rays. In star-forming galaxies, supernova remnants and bright X-ray binaries help power these emissions. When star formation stops, fresh supernova remnants cease to appear, and the most luminous high-mass X-ray binaries fade as their massive companion stars die. What remains are older systems, white dwarf binaries, low-mass X-ray binaries, and the residual emission from the central black hole if it still accretes matter. The galaxy's radio glow from cosmic rays interacting with magnetic fields gradually weakens as the most energetic particles are lost. X-ray luminosity declines as the stellar population ages and compact binary systems merge or quiet down. Over immensely long timescales, the galaxy's high-energy signature softens and dims, shifting the overall energy output increasingly toward low-energy infrared and microwave radiation. Observed from afar, such a galaxy appears not only redder and fainter in visible light, but also more subdued across the entire electromagnetic spectrum, echoing the broader cosmic trend toward lower energies. Even in a galaxy where no new stars form, interactions among existing stellar remnants continue. Binary systems containing white dwarfs, neutron stars, or black holes slowly evolve under the influence of gravitational radiation and tidal forces. White dwarf pairs can spiral together over billions of years, sometimes merging quietly, other times igniting thermonuclear explosions if their combined mass reaches a critical threshold. Neutron star binaries and black hole pairs also lose orbital energy through gravitational waves, eventually coalescing in sudden compact mergers. In an otherwise calm galaxy, these events are rare but significant, releasing bursts of energy that momentarily puncture the growing darkness. However, they do not create new long-lived stars or replenish star-forming gas. Instead, they convert two remnants into one, slightly reducing the number of luminous or potentially luminous systems. The galaxy's energy budget becomes dominated by such sporadic, brief flares against an increasingly dim background, like the last sparks in a slowly cooling fire that no longer receives fresh fuel. On large scales, the structure of an aging, quiescent galaxy still changes, but on timescales that stretch across tens or hundreds of billions of years. Without the continual injection of energy from supernovae and giant molecular clouds, the disk thickens gradually as stars and remnants scatter off one another and off clumps of dark matter. Spiral patterns, if they once existed, can slowly fade as stellar orbits become more randomized. Bars in disk galaxies may weaken or dissolve over long periods, or in some cases grow more prominent before eventually losing contrast. Globular clusters orbiting in the halo experience tidal forces that strip stars and spread them into elongated streams. The central regions may grow denser as dynamical friction draws heavier objects inward, feeding the central black hole or building a concentrated core of stellar remnants. All these changes proceed with no sudden bursts of new starlight, only the steady reshaping of orbits in response to gravity, gradually altering the galaxy's appearance as its light ebbs. Between galaxies lies a vast reservoir of thin, hot gas that threads galaxy groups and clusters. In the earlier universe, some of this gas could cool, condense, and be drawn into galaxies, providing fresh material for star formation. As cosmic time advances and the universe expands, this intergalactic medium becomes more diffuse. Its density drops, and its temperature remains relatively high, sustained by past shocks from structure formation and galactic outflows. In a cosmos where star formation has largely ceased, much of this gas never finds its way into new stars. It instead expands with space, thinning further and slowly cooling by emitting X-rays and ultraviolet photons. The connection between galaxies and their surroundings weakens because there is little flow of cold gas inward and only modest outflows outward. This changing balance locks in the aging state of galaxies, isolating them in a more tenuous, gently fading environment that no longer easily supports the luminous cycles of birth and death that once defined cosmic history. Small collections of galaxies, called groups, are bound together by their mutual gravity. Over time, interactions within these groups can lead to slow but profound changes. Galaxies orbit one another, exchanging tidal forces that draw out long tails of stars and gas. Dynamical friction causes the more massive galaxies to sink toward the center of the group potential, while smaller ones may be flung outward or gradually merged. In a star-forming era, such encounters can compress gas and trigger new stellar births. Once star formation has largely stopped, these interactions mainly rearrange existing stars and remnants. Some galaxies are entirely absorbed into larger neighbors, contributing their stars to extended stellar halos. Others are left as diffuse, dim systems stripped of gas and much of their outer stellar material. The group as a whole becomes dominated by a few large, quiescent galaxies surrounded by faint streams and orphan star clouds. The luminous variety of many distinct, shining members gives way to a quieter, more centralized configuration. Mergers and close encounters between galaxies leave behind delicate structures known as tidal streams. These are elongated ribbons of stars, dark matter, and sometimes gas, pulled out by differential gravitational forces. In an aging universe with reduced star formation, such streams become some of the most visually striking, though faint, vestiges of past dynamical activity. Without bright, newly formed star clusters to light them up, tidal streams slowly fade as their stellar populations age and redden. Over billions of years, the stars along these streams spread further, diluting into the general stellar halo. Yet careful observation can still reveal their presence as slight overdensities or as coherent motions against the background. They trace the paths of former dwarf galaxies or outer disk material that has been consumed. In a galaxy no longer birthing stars, these streams act as ghostly handwriting in space, recording the history of accretion and interaction long after the dramatic phases of collision-induced starbursts have ended. Throughout all these changes, an unseen component remains largely unaffected by the end of star formation: dark matter. This elusive substance outweighs ordinary matter in galaxies and clusters, shaping their gravitational potentials. While stars, gas, and remnants trade energy and rearrange themselves, the dark matter halo maintains a relatively stable distribution on galactic scales. Its particles interact primarily through gravity, not through radiation or collisions like gas. Because dark matter does not cool by emitting light, it does not clump into smaller, brighter structures in the same way as baryonic matter. As luminous components fade, the dynamical importance of dark matter becomes even more pronounced. Stellar orbits and the motions of remnants increasingly reflect the underlying dark halo's shape. Over very long timescales, some gradual evolution may occur through interactions with baryons and through mergers of halos, but the general picture persists: a massive, invisible framework supporting ever-dimmer islands of stars, remnants, and gas in a universe where new light is becoming scarce. All of this unfolds against the backdrop of the cosmic microwave background, the afterglow of the hot Big Bang. Today, this radiation bathes the universe at a temperature of roughly 2.7 Kelvin. As the universe expands, the wavelength of this background light stretches and its temperature steadily drops. In the distant future, it will become even colder and fainter, shifting further into the radio part of the spectrum. For galaxies that have stopped making stars, the cosmic microwave background remains a pervasive, though weak, source of radiation. It sets a kind of minimum temperature below which isolated objects have difficulty cooling. As that floor drops, white dwarfs, neutron stars, and planets can continue to lose heat, though ever more slowly. The contrast between the light of galaxies and this background also changes. Where once galaxies shone brightly against a relatively warm cosmic glow, they eventually become faint, red islands set within an almost perfectly dark and cold sea of stretched, low-energy photons. In galaxies that no longer form stars, the remaining light carries a compressed record of everything that came before. The distribution of stellar ages reveals when star formation peaked and when it declined. The ratios of elements in old stars preserve information about how many supernovae exploded and over what period. The spatial arrangement of different stellar populations reflects ancient mergers, accretion events, and internal instabilities. Even the abundance and types of stellar remnants hint at past stellar initial mass functions and environments. As the universe continues to age, accessing this memory becomes more and more challenging because the light grows fainter and redder. Yet, in principle, every photon escaping from these old galaxies still encodes some aspect of their long history. Eventually, as the last long-lived stars slowly exhaust their fuel and remnants cool toward near invisibility, even this luminous memory will weaken. The universe edges toward a state where its rich narrative of star birth, evolution, and death is written mostly in structures, motions, and the lingering gravity of what once shone. In a galaxy where star formation has long ceased, the remains of earlier generations continue a slow drift through space. Loose debris from ancient planetary systems, cometary bodies, and shattered asteroids circles unseen around long-lived red dwarfs and fading white dwarfs. Over tens of billions of years, repeated gravitational nudges alter these orbits, gradually spreading material into diffuse belts and toroidal clouds. Occasional collisions still occur, but they are rare, low-energy events, more like gentle rearrangements than dramatic impacts. Dust from these encounters adds to the thin interstellar haze, now too sparse and warm to collapse into new stars. In some systems, remnant planets spiral gradually inward as tidal interactions with their aging stars rob them of orbital energy. In others, distant objects are slowly ejected into interstellar space, adding to the population of rogue material wandering the galaxy. The once vivid cycle of rapid star birth and violent destruction has become a muted circulation of remnants, where gravity reshapes what exists but no longer kindles fresh nuclear fire. As the stellar population of an old galaxy thins and cools, gravitational encounters between its remaining components continue at a measured, patient pace. Star remnants, surviving stars, and small black holes pass by one another, subtly redirecting their paths with each close approach. Over extremely long timescales, these tiny changes accumulate, trading orbital energy and angular momentum across the galactic system. Some stars are slowly pushed outward into the far halo, where they circle the galaxy on enormous, elongated orbits. Others sink gradually inward, drawn toward the dense central regions and the dominant supermassive black hole. Binary systems can be separated or tightened, and a few compact pairs may eventually spiral together, releasing a brief, final burst of gravitational waves into an otherwise quiet cosmos. The overall structure of the galaxy remains recognizable, but its internal architecture shifts, softens, and relaxes. In the absence of new stars, these gravitational interactions become the main sculptors of the galaxy's aging form, steadily rebalancing mass without adding fresh sources of light. For any hypothetical observer living in this far-future universe, the night sky would offer a very different scene. The bright, richly patterned Milky Way band that once cut across the sky would have faded into a sparse scattering of reddish points. Most of the luminous blue and white stars would be gone, replaced by long-lived red dwarfs barely visible to the unaided eye. Intervening dust and gas clouds would contribute little glow, having dispersed or warmed beyond the point of forming vivid nebulae. The surrounding galaxies that once populated the sky as faint smudges would be more distant and redshifted, some carried so far by cosmic expansion that their light no longer reaches the observer's location. The background glow of the cosmic microwave radiation would have cooled and dimmed to an almost undetectable whisper, yet the sky would not be perfectly dark. Isolated white dwarfs, neutron stars, and rare late-time mergers would still punctuate the darkness with subtle points and brief transients, quiet reminders of an earlier, brighter cosmic era.